treatment for this, which can help us to deduce some concept we cannot see from Newtonian mechanics directly, right? So we'll start with something called Lagrangian mechanics. So the main point here is that they have something called generalized coordinates. Which we already know what is coordinates. For example, x, y, z. These are the coordinates. And we know that it plays a very important role in the mechanics, right? And we are going to call it qi. I can be from 0, 1, 2, maybe 0, 1, 2, if it's three-dimensional, which means just x, y, z, right? qi. You also have something called generalized velocity. These are the basic variable, okay, or independence variable in this framework. Of course, we also know what is velocity. Velocity is just the rate of change of your position. That is the velocity. So naturally, we will say this must be qi dot. Okay, so I have quantity. I just define the quantity. If it's one-dimensional, then I have q0, just q, and then with q dot, which talk about the rate of change of qi. Okay, so we have this two quantity, nothing special, right? We already know what is position and what is velocity, and we use it in the Newtonian mechanics. But in Lagrangian, it has the it starts from here, and the main point is if qi, all the qi dot specify. Right? If I know what is the Q and Qi of your system, then the system is determined. It's unique. Right? I can describe the state completely already. Do you agree? It's just like what we feel in classical mechanics, right? But it's just now that we need to make it generalized. It's just not a real coordinates, it can be a real coordinates, a real velocity, but it can be other quantity also. Okay? But we will see later, right? Now, then, here we say that it's based on something called principle of least action, which we are not going to go through this math. It's not useful for us. We just want to know the results. We base on the principle of least action. Right. This is basically just an integration, okay? And what do we get? We say that every system is characterized by a function called L. So it is characterized by this L is a function of Q1, Q2, right? Q1 dot Q2 dot and T. The time, the generalized coordinates, and the generalized velocity, and this L function, we call it Lagrangian. Okay? And this principle of least action tells us that the so-called least action is an integration. Now, why we want to say this? We are not going to very deep, but if you go to quantum mechanics, you will find that everything developed from the classical mechanics. They also have something called action. And just like classical mechanics, here the action means if I go from T1 to T2, from time 1 to time 2, and if I do an integration on this Lagrangian over time, this must be minimized. So what does it mean? It means that you can come up with any function, Lagrangian. You say, okay, my system, I feel that is described by this function. This function is dependent on this variable. But which one is the true solution, the true function describing how this system evolved? Is the one that gives you the smallest action. And the action is the integration of this Lagrangian over time. Do you see what I mean? Not really, right? But doesn't matter. It's not in this class. So, so my goal is this. Oh, actually, I need to go to the next page. Yeah. Doing the integration, you can have different L. For example, you say your L is 2q squared. But 2q squared might not give you the minimum value when you do this integration. Maybe 2q give you the minimum value. Then 2q is the correct Lagrangian of your system. Right? So this principle of this action is that this, what we call it functional, right? This function, this whole thing is functional. This function is correct when this one is minimum. Okay, so talking about this, I think it can be confusing, but we don't need to go deep, right? In the future, if you want, then you come back, right, for your future study. I know that this is confusing, but I try to say it is, I hope you understand, this one is just a function, okay? And you want to find out what function will minimize this. One thing maybe, I don't know if you remember from your optics. If I have a light coming here and then reflect from A to B, why it reflects? One possible explanation is that the time you travel from A to B is the shortest if you get reflection. If you try to come up with, say, I think that it's not going to reflect, it should travel a straight line, you find out that actually this time is longer than this one with reflection. This is also principle of least action. The other way for you to derive the Snell's law. Have you learned about this before? Heard about this? If no, just that the reflection can be understood as the nature want to go through the shortest path in their process. So when you go from A to B, it turns out that I go here first and then do a reflection. It's shorter than this. Because the traveling speed in the water, for example, is lower than the air. So I would rather spend more time in the air and then have a shorter distance in the water. So this is something similar, right? Although it's high dimensional, is that which path we should use for the system to evolve from state 1 from state, let's say Q at T1 to state at Q at T2, right? Basically, I say I try to hit this billiard ball and it's going to move, right? I know that initial position is here. I know final position it is at this corner. But which path should it travel so that it minimizes this action? Then maybe you'll find that straight line is the farthest. And you will find that this will fulfill all the Newton's law. Okay? Something like that. Okay. But let's ignore this. Just remember there's something called principle of least action. If you need that, go back to read it. And this is the one that gives us something very important. We find that the Lagrangian can be decomposed into two parts. Kinetic energy minus the potential energy of a system. It turned out that the Lagrangian is the kinetic energy of a system minus the potential energy of a system. Okay, we did not prove it, I just show you. Okay, which we will write it as T minus V, usually. Okay. And because of the principle of least action, we also have something called Lagrangian equation. What is this? It says this, d dt partial L partial Q dot minus partial L partial Q equals to 0. And maybe I should add I, because you might have different I, right? For each I. So I can be X, Y, Z, right? But not just X, Y, Z, because we can have many particles. And we are talking about generalized coordinates. So it can be angular velocity versus the angle, which is also a generalized position and generalized velocity. Okay, so what did we learn so far? Nothing. We talk about, I hope you understand, we have so-called generalized coordinates, generalized velocity, which later in Hamiltonian is something similar. And you will find that we apply this generalized coordinates and velocity to a qubit. It also has something similar. That's called conjugated variable. So these two variables are not conjugated yet, but yeah, it's conjugated. But the point is that you know that they based on two quantities. Here, only generalized coordinates and generalized velocity. Yeah, something called least action principle. If you don't understand, fine, don't memorize it. But try to use this light reflection as a guidance to you. I hope that you have this concept. And then, after all the math we did not show here, we find that Lagrangian equal to the kinetic energy minus the potential energy. And also the least principle of action tells us that the Lagrangian should satisfy this equation. But again, what is Lagrangian? It is the law describing how the particle move, how they work, right? So therefore, the L is going to tell me how it works, right? I will show you with example. This is still a little bit confusing, but I want to also define one more thing. Besides the generalized coordinates and the velocity, we can also define a generalized momentum, right? It does not need to be the momentum that we are using, but it is defined as the partial derivative of partial Q, then that is the generalized momentum. Now, maybe let's quickly do a check, right? Naive check. To see if this makes sense. For example, I have a system, right? Or let me just call it a particle. Let's say I have a particle. At Q, single particle, with velocity Q dot. Is this okay? I have particle at position Q moving at velocity Q dot. That is okay? This is just a real regular coordinates and regular particle, right? What is the kinetic energy of this guy? When you move, say again? Half mv squared, so it is half mq dot square. Do you agree? Half mv squared. How about the potential energy? Okay, that you assume that it is falling down, right? But actually we don't know. Actually, I would say it's just a position, function of the position, right? On the hill or whatever. So what is the Lagrangian of this guy? Ke minus PE, as I told you earlier, the kinetic energy minus the potential energy. Just definition, okay? Not definition, I mean just the result of the Lagrangian equation, okay? So what is this? 1 over mq dot square minus uq, correct? I want to find the momentum. Based on what I say here, partial on the top, what is the momentum? P equals to partial L partial QI dot. Correct? I gave you. This is the definition. So if I do a differentiation on this, look at this is partial derivative. The U has nothing to do with QI dot, right? I have an independence variable, Q and QI dot, Q and Q dot. This is just Q, right? So you differentiate, partial differentiate this with QI dot, this is become 0. Okay. Then how about this term? MQ dot. What is MQ dot in our regular sense? MV, right? So again, it's the momentum. I just show you that it makes sense. So by using this formalism, I come back to regular Newtonian mechanics. It includes this set. Is this okay? Yeah. Sorry, this is the typo. Not typo. This is PE on top. This is only UQ. Oh, because when you say this is U of Q, right? It means maybe I have something like this. 1 plus 2Q plus KQ square, but I don't have Q dot. So when I do partial derivative on the Q dot, I don't have Q dot. Everything becomes 0. Because, as we said in this formalism, Qi and Q dot are two independent variables. Yeah, good question. Okay, yeah.
The time has to be a variable for the Lagrangian?
Time is the variable, yeah.
You have to have the independent variable to complete.
Correct. Yeah, but
space, time.
yes, but very often this time it is Lagrangian is independent of time. For example, look at this one. It kind of no. This is dependent. But sometimes independence, then you will be able to derive, if I remember correctly, when it's independence of time, I think you get conservation of energy, right? And if it's independence of space, you get conservation of momentum. Am I right? You studied before?
Translational symmetry.
Translational symmetry. Right, yeah. But we don't go to those details, okay? Good. Now, so what do we need to get from here in your exam? Maybe not much. I might not even do this in exam. I will do this in homework. But what you want to get is you understand everything is governed by the Lagrangian equation. And then you have a few important definitions, like what is the generalized momentum. And then this is good to memorize. Usually, it is kinetic energy minus the potential energy for Lagrangian. And that's it. Okay? So let's do some exercise. Free particle. What is the meaning of free particles? It means there is no potential energy acting upon it, right? So for a free particle moving at velocity v at location x, right? What is the Lagrangian? First, what is the kinetic energy? We just say that half mv square. I just use a scalar form, not vector, because it's one-dimensional in this case. Just consider one dimension, right? What is the potential energy? What is the potential energy of free particle? 0, right? So the Lagrangian is very simple. Half mv square minus 0, which is half m. But I try to go back to the notation. I call it q. V equal to q, right? Just velocity equal to q dot. Okay? So with this, I want to find the equation of motion. How is this particle going to move? Then I use the Lagrangian equation, right? Lagrange equation that we learned earlier. Again, this one, if you forgot. This one, okay? It's easy to memorize because it must have something related to the partial L, partial Q dot, right? It also has a term partial L, partial Q. And then for the Q dot one, I further add d dt because partial Q dot is like partial Q. This is dq dt, right? I can cancel dt, then you have the correct units. So that's the way I memorize it. So what is partial L, partial Q? Based on this equation. It means I'm going to do partial L, partial 1 over mq dot square, partial Q. What is this? 0, right? Because again, Q and Q dot are independent variable, conjugate, right? So this is 0. Okay? How about partial L, partial Q dot? You just told me, which is mq dot, okay, which is mv. But then I need to further do it with d dt partial L partial Q dot. So I do one more time derivative. What do we get? mq dot dot, sorry. mq dot dot, right? Second derivative. One dot is 1 dt. Is this okay? So what is the equation of motion? mq dot dot minus 0 equal to 0, which is mq dot dot equal to 0, which is ma equal to 0. Is this correct? For a free particle. What is ma? M times a, how about? Force. F equal to ma. Come back to Newton's equation. This is Newton's first law. There is no acceleration, no force, right? So you see that I don't need to understand all the basics. I just start with the kinetic energy and the potential energy. I find the equation of motion. This is the equation of motion of this particle of this free particle. It means that you just travel at velocity v forever because no acceleration. And why no acceleration? Because no force. And why? How can we incorporate that? Because the force determines the potential energy. Okay? So this is a simple one, but you will see that, okay? Now let's do a more complicated one to appreciate why this is helpful compared to Newtonian mechanics. How do you solve the simple harmonic oscillator? What is a simple harmonic oscillator? We might attach a spring to a mass m, and this is moving a velocity v, and maybe at the position x, right? Maybe we start with the midpoint as 0, and then here's x, right, minus x, right? And it has the Hooke's constant for the spring. So we know that what is the kinetic energy, right? What's the kinetic energy of this one? Still just 2½ mv squared. So it's just half mv squared, right? Because I don't care what you are, whether I'm hanging to anywhere, I'm traveling at a velocity of mv squared, of v, then I have half mv squared, right? So this gives me half mq dot squared. Same as last time, right? Same as the free particle. Is that okay? How about the potential energy? Potential energy, I require you to just recall from your undergraduate physics, right? The potential energy due to a spring is what? Half kx squared. Okay, that's the potential energy. Yeah, you have this potential, right? Because you stretch it to the left, to stretch to the right, you do have this potential energy. So the Lagrangian of this system equals to half, and this I don't want to write x, I write as q. I just like this, just an exercise to make this very generalized. M q dot square, and then what's the Lagrangian, remember? Kinetic energy minus potential energy. Right. Okay? Which one equal to which? We don't know yet. Here it's just the kinetic energy subtract the potential energy. So it will, yeah, so it is the difference in the kinetic and potential, right? So at the 0, you have the maximum of kinetic. At this maximum x, you have the maximum for potential. Yeah, it's a difference, but that is not the main purpose, because the Lagrangian is just the difference between KE and PE. Okay. Then how do I find its equation of motion? Again, d dt partial L partial Q dot minus partial L partial Q equals to 0. Okay. So what is partial L partial Q? Based on this one, what is partial L partial Q? Minus KQ, very good. So how about partial L partial Q dot? We just studied, right? Which is the momentum MQ dot. And as a result, d dt partial L partial Q dot equals to MQ dot dot MA, right? Okay, very good. So what is the equation of motion? MQ dot dot plus KQ, not minus, right? Because I need to subtract dq dq, dl dq equals to 0. That is the equation of motion. And you derive this in undergraduate, maybe high school, right? This is just like mx dot dot plus kx equal to 0. Right? And we can also call it as x dot dot plus k over mx equal to 0. Just divide it by m, which is x dot dot plus omega square x equal to 0 if I define omega equal to square root k over m. And if you still remember, if you did take this simple harmonic oscillator, right? This is the equation of motion. You see that this is so easy. But more importantly is this is very mechanical. If you come up with a system that you don't understand, I tell you that this is the generalized coordinates and that is the generalized velocity, you will be able to come up with the equation of motion for that system. Now, if I have a superconducting qubit, I tell you the charge is the, I forgot which one actually, the capacitance is the capacitance energy is the generalized, I forgot coordinate, I need to review. And then inductor is the generalized velocity, for example. You have the same formalism. You will be able to derive the L16 equation in the same way. The point is, what is the expression of the generalized coordinates for your circuit? Now, not just for this, the point is later we learn Hamiltonian. Then we have a quantized version. And naturally, you will have a quantum version of your electrical circuit. Right? We will learn that later, but now just a preview. Right? I just want to show you, this is a mechanical derivation, right? A very nice step-by-step. I don't need to understand this system at all. I just need to know its kinetic energy and potential energy. Then I can get all the equations of motion. Okay? But we are not going to solve it. We no need to solve it. we know that this equation will give us x equal to, for example, right, x of t. If I put it in the complex, it will be something like this. These are the general solution, yeah, harmonic oscillator. That's why they're harmonic. Any questions?
So now,
You can do that, yeah, because you can find the kinetic energy of electron, potential energy, and then you go through this. So for any system. But this is not great enough. We have everything called Hamiltonian mechanics. And why